Hi, students. This is a lecture on chapter 29 on quantum theory. Okay, so in this chapter, we continue our study of modern physics. Okay, and again, modern physics is the physics of the 20th century. So, and I alluded to why we need to talk about modern physics. I mean, at the end of the 1900s, as evidenced by the speech given by Lord Kelvin, the State of the Union, we had this idea that everything was pretty much figured out. We had, I mean, to his credit, to the credit of the physics community, there were some stalwart theories that covered a wide range of physical phenomena, and they were very, very successful. So you had mechanics, Newtonian mechanics, was very successful in describing all motion, both translational, rotational, and vibrational motion, as well as in all three states of matter: solid, liquid, and gas. And we also had a very successful theory of thermodynamics and a kinetic theory of gases that very much described phenomena dealing with heat transformation, temperature, energy transformation. Then we, of course, have what we talked about in this entire semester is electromagnetic theory. Electromagnetic theory is shows that there's the greatest amalgamation of all the physics, of all phenomena of electricity, magnetism, and light are all manifestations of the same, of just five equations, four Maxwell equations and electromagnetic force law. So, with all that said, I mean, we can understand Kelvin's great confidence, but as he said, the speech was a two-cloud speech. On the horizon, we're just two clouds. He's got to work out. He's got to work them out. And it turns out there are two revolutions. One was the special theory of relativity, and the other one's quantum theory. Okay, I should say, let me back up. One of them was relativity, and the other one's quantum theory. All right. Now, let me be more specific here. What we talked about in chapter 28 was the special theory of relativity. That's the theory that deals with what happens to physics when you discuss it in reference to what's called an inertial reference frame. That is, the reference frame is of one observer is moving with respect to another at a constant velocity. There are no accelerations in special relativity. Okay, and so as you saw, physics needed to be fixed up. Newton's mechanics was wrong for low speeds, actually for high speeds. I apologize. But that was one of those 2 out of 4 Einstein's great papers of 1905, and the Anna Mirabilis dealt with the special theory of relativity. But that was but that's not where Einstein ended with relativity. When he considered accelerations and forces and the understanding of gravity or gravitation, that was the general theory of relativity. And he worked in that for about 10 years. He came up with the general theory of relativity in about 1917. And that gave, Newton told you, well, we had a universal law of gravitation. Force between two masses is mass 1 times mass 2 times is capital G divided by r squared, the center distance. But Newton, he could calculate what the gravitational force was, but he had no way of understanding how gravity, how gravitation, how something like the sun, which is 93 million miles away, could affect so can so greatly affect the Earth or all the other planets? How does gravity work? Well, Einstein explained that. That's called the general theory of relativity. And that requires a level of mathematics well beyond those of an undergraduate physics major. We're not just talking about, well, do you have calculus? No, we're talking about having an entire degree in mathematics and going to a graduate level of mathematics to understand the tensor calculus of the general theory of relativity. So again, we will not even attempt to even discuss that in this class. In fact, we don't talk about general relativity at all. But when I say relativity, I mean not just the special theory of relativity we study, but also the general theory of relativity. And then quantum theory, which is what we're going to talk about. And quantum theory is that physics are very small, the submicroscopic, in fact. And then the following two chapters, this is chapter 29, the following two chapters will be the physics of the applications of quantum theory, chapter 30 and chapter 31, nuclear atomic physics, nuclear physics. So again, chapter 29, as I just said, is quantum theory. And then we have the applications of quantum theory. And that is, again, I'll write this down, it's submicroscopic. Well, you go smaller than that, well, you have atoms, which are on the order of angstroms or 10-ish nanometers. So chapter 30 discusses atomic physics. That's the physics of the atom, and of course, absolutely requires quantum theory, and, or we say atomic physics. And finally, we finish the course up with chapter 31, which is nuclear physics. And of course, a nucleus is much, much smaller than an atom. So if quantum physics applies to the atom, it certainly applies to the nucleus. All right, so there you go. That's the rest of this course. All right, so let's develop what we call quantum theory. Now, again, I talked about motivation of quantum theory back in the beginning of chapter 28, leading into what we're calling modern physics. I do not desire to repeat it. Again, we're going to see a lot of applications where we're going to apply quantum theory to the test. Okay, so what is quantum physics? What is it? So often it's oftentimes called quantum physics, quantum mechanics, quantum theory. So again, any of the terms are more or less interchangeable. So quantum mechanics is the branch of physics that deals with microscopic objects. Quite simple. So quantum mechanics, again, I haven't really told you anything but the size of the objects that are required. So quantum mechanics is the branch of physics which deals with submicroscopic objects. It's not a choice. You must use quantum physics. The classical physics that we've studied up to this point, if you exclude relativity, of course, does not work at the microscopic or submicroscopic level. It's not a matter of choosing to use it or not. It is a matter of being required to use it. Classical physics, or what we call classical physics, Newtonian mechanics, electromagnetic, classical electromagnetic theory, none of that works in the submicroscopic realm. All right, now there are certain aspects of quantum mechanics that are familiar to us, right? I mean, quantum mechanics is unfamiliar, because submicroscopic objects are smaller than we can observe directly with our senses. We generally only observe with the aid of instruments. Quantum mechanics the quantum mechanical effects are more or less foreign to us. well as foreign as relativity. So again, since quantum physics deals at the submicroscopic level, and we cannot generally experience its effects with our senses, and thus requiring instruments. Quantum mechanics is foreign to us, or these effects are foreign to us. Much like relativistic effects. Relativistic effects, our problem is we don't experience things at high speeds, right? We just don't, even the highest speeds that we can ever experience with macroscopic objects, like hypersonic aircraft, for instance, are nothing compared to the speed of light. Well, we don't ever, our senses cannot directly experience the submicroscopic. So because of that, quantum physics is also, the quantum realm is also unfamiliar to us. However, we can understand things that are quantum. However, I mean, there's quantization in our regular lives. So the word quantum comes from the word quantize or quantization, right? So the word quantum comes from quantization. Meaning that things come in units or lumps, as Richard Feynman would say. All right. So you say the average household has 2.5 children. I've heard that said many times. Well, again, that's a statistical average. You're not going to see a family that has 2.5 children. You're not going to see somebody that has, oh, you have a half a child. I mean, again, that doesn't make any sense. Children come in lumps. They come in units. All right. So again, average family size has 2.5 children. Again, that's always the statistics. You have one family that has 2 children, another family has 3 children. You average them out, they have 2.5, right? Or, but you did it over millions of people. All right. Well, clearly, children come in units or lumps. All right. You're not going to have a half a child. But statistically, you'll get something like this. You say statistically, average all families across the United States. How many children do you have? How many children do you have? Add up all the children, divide by the number of families, and typically, as I've heard the term, it's typically around 2.5. Okay. Money. Money is quantized. So money, all monetary figures are expressed as pennies. So the penny or the cent is the basic unit of money. So, and again, it makes no sense to say 14 1/3 cents. And that doesn't make any sense at all. Because money comes in lumps. In the basic money, even you're talking about hundreds of dollars, thousands of dollars, whatever, in the most basic sense, you cannot get any more of a unit of money than the cent, the penny. All right. And so we do understand how things are built up. We've talked about electric charge, electromagnetic theory. We know that all charges are the summation of individual fundamental charges, right? So if you go to physics, we talk about charges, for instance. All right. So all charge is composed of integral multiples of the fundamental electric charge. Q sub E, we recall 1.60 times 10⁻19 coulombs. So you're not going to get a fraction of a charge unless you're a quark. Again, we don't usually deal with quarks. I mean, in the macroscopic world or even in the microscopic world, we deal with fundamental charges. Again, fundamental charges are all, I don't care what charge you give me, it's going to be so many Q sub E's. It'll be N, capital N is the number of charges times Q sub E. All right, so again, everything is fundamentally quantized in charges. So charges are quantized. Atoms, molecules, electrons, photons, protons, they're all quantized. All right, so even atoms. So again, atoms, molecules, electrons, and protons are all basic physical entities that are quantized. And we accept this. So that's basically saying that things come in lumps. So for instance, we see a stream of water. And of course, do not see individual molecules. But this is because the water molecules are so small and so numerous. Okay, so we go to the macroscopic world, but we know that it's composed of the microscopic world. So this concept of recovering classical physics from the physics of the submicroscopic is called the correspondence principle. That's due to a great physicist by the name of Niels Bohr, who many people have considered the father of quantum mechanics. And so we see that, yeah, when you look at a stream of water, we can't see the individual atoms or the individual molecules, but we do know they're there, and we do know that they're so small, too small for our senses, and so numerous anyway. All right, and so again, there's the correspondence principle. We'll talk more about this in a moment. The correspondence principle due to Niels Bohr, and we'll talk a lot about him, is a concept that we can recover macroscopic physics from microscopic physics. And we'll see in a number of ways how this works. So in our example of the stream of water, well, we turn on a water faucet and we see what we would typically see as your prototypical stream of water that you would see at any point in time in your life, whether you've taken physics or not. But we all know that to really understand water requires quantum physics, or quite frankly, it requires atomic physics. But we can understand from the correspondence principle that you can go from microscopic physics and essentially expand into macroscopic physics. I mean, so kind of like, we looked at relativistic energy, relativistic momentum, or relativistic kinetic energy, relativistic momentum, things like that. We saw that, well, as we progress to lower speeds, we see that how the relativistic formulas transform into the classical formulas. The correspondence principle is your way of saying, well, we're in the physics of the macroscopic, which we will call, or submicroscopic, which we will call quantum physics. Quantum physics, when you relax the, it being forced to be in small, in very, very small space in that regime, and consider larger spaces, the quantum physics should naturally melt into the classical physics. That's what a correspondence principle means. All right, so again, now we take, for instance, electrons, protons, atoms, and molecules. We understand those to be quantized. You understand that, let's say there's a quantized mass of these particles as well. So mass is also quantized. But what's surprising in quantum mechanics is some other things that are quantized that you might not expect to be quantized. All right. So again, we know that, we know that the mass and charge of fundamental particles is quantized. But the surprise that quantum mechanics provides us is that other things that we don't expect to be quantized are quantized. So the surprise in quantum mechanics is that other quantities that we don't expect are quantized. Do not expect to be quantized or quantized. And some examples of this are energy and angular momentum. We do not see the quantization of energy or angular momentum in our macroscopic world. That just doesn't happen. But we're going to find out that in quantum mechanics, those entities are truly quantized. Energy comes in lumps, and so does angular momentum. All right. So again, as we move on, quantum physics provides these surprises to us. Okay. So let's start off by seeing how we more or less kind of tripped into needing quantum physics. All right. And so again, I mentioned one of the unanswered questions of the 1800s leading into 1900s was the what we call the blackbody radiation. All right. So basically, we're going to find out that from blackbody radiation, the energy is quantized. So what does this mean? All right. And so let's kind of talk about, before we get into the actual experimental evidence, blackbody radiation, let's kind of think about what quantization of energy actually means. So energy is quantized in some system. Now, again, going into 1900, first, we had no idea about any of this. All right. So energy is quantized in some systems. That means that the system can only have certain energies and not a continuum of energy. Okay. So, which means that the system can only have certain energies. And not a continuum of energies. That we see in the classical case. So what this means is that energy can only take on certain values. All right, so you'd only have, and they can only come in certain, certain quantized values, and they can only, and the difference between one energy and another is also quantized. No, we don't see that in the classical world. I mean, I can write down kinetic energy of something, a moving object, and it's not that there's not discrete values that are allowed for the kinetic energy of an object. Any value is fine. So this is very much different. This would be like, so kind of give you an analogy of how weird this is. All right. So that energy can only occur in certain lumps or certain quantized values. So here's some analogies. So we can draw some analogies if this helps. So some analogies that might help would be, it'd be like having only certain speeds of that the car can travel, because its kinetic energy can only have certain values, right? So it is like your car can only travel at certain speeds. Because the kinetic energy is quantized. Okay, so for instance, maybe your car can only travel at, here's the speed your car can travel at, and maybe your car can only travel at, say, let's say the speeds are in meters, say meters per second. Well, your car can only travel, let's say 5, 10, 15, 20, 25, nothing in between. You take a quantum jump to get from one to the other. So your car automatically, boom, it jumps at 5 miles per hour. And then at some point, boom, it jumps to 10 miles per hour. It doesn't take on the values of 11 or 12 or 13 or anything, or 12.23 or any other values. It only jumps. It only is allowed to have certain quantized values. Again, we don't see that in our regular world. We don't see anything like that in the regular world. Only certain quantized values are acceptable. Let's say, again, I'm drawing an analogy. We don't see this, right? But you see this in the quantum mechanical world. All right, because let's say kinetic energy would be quantized, and so your car would only be able to take on certain speeds, because why? That kinetic energy is 1 FMB squared. And that's one example. We do not see this in our regular life. All right, and so we do not see this in the classical world. So again, we do not observe such behavior with energy in the classical world or microscopic world. Okay, we don't see this behavior. Okay, so how do we even begin to care about this? I mean, how do we even begin to even notice this? All right, so essentially, we start off by looking at what's called blackbody radiation. All right, so in at the turn of the 20th century, we had one big unanswered question. Or, well, we had several. At the turn of the 20th century, we did not understand what is called blackbody radiation. So if you look at, again, you have to go back to physics 1. So recall radiation heat transfer in physics 1. Okay, radiation heat transfer in physics 1. We had the understanding that the radiated power, we learned that radiated heat or radiated power was given as, and going back to physics 1, so we have an object that has a certain temperature. Radiated power is given as sigma E A T to the 4th. And that's something we studied back in physics 1. You know, sigma is a Stefan Boltzmann constant. (5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4th. Again, when you're talking about radiation transfer, you must do it in Kelvin. E is called the emissivity. That's a number between 0 and 1. It is unitless. It's how good of an emitter. So a reflector has emissivity of 0. What we call a black body is a perfect emitter. It appears jet black. That's why it's called a black body. So a black body, the perfect emitter. So its E equals 1. Again, there's no units to E. 0 to 1, it's some value between 0 and 1. Anything between is called a gray body. All right, and the A is the surface area. So if we're talking about the sun, for instance, it'd be the surface area of a sphere, right? And so again, it's the area, the radiated area. Well, we understood this empirically. We do not in any way understand how you can get this formula. Okay, there is no theoretical basis for this formula. Now, you want to go back even further. You want to look at the at what's called the radiant intensity. All right, and so again, you integrate the radiant intensity to get this power. Again, it requires integral calculus, but the reality is we tried to figure out the radiant intensity. Okay, and so we tried to set up a perfect emitter, a perfect black body. And the idea is we had a cavity. You think of a cavity as you know, so some sort of a sphere, but you basically have a cavity. Cavity has walls. And the cavity walls are held at a temperature T. Okay, so again, the cavity has walls. This is a cavity whose walls are held at temperature T. Okay, so the walls inside here are held at temperature T. And it's a cavity that we understand very well. And there's in this cavity is a little tiny hole. It's a little tiny hole in this cavity. Small enough we can actually sample this hole. So very little electromagnetic waves will escape this hole. All right, so it's a little tiny hole. So we can sample the radiant intensity from a tiny aperture. The aperture is small enough not to affect the experiment, not to affect the system. Okay, so we don't affect the system. However, we can sample the small amount of radiation that escapes this hole and know that this represents the entire inside of the cavity. It represents the system. Okay, so there is, if you look at this cavity, it is black. There is only this little tiny hole where things escape and nothing else. All right. So it is considered what's called a black body. All right. And so with this said, this was studied. And essentially the results ended up being absurd. All right, so again, how you studied it was, well, light's an electromagnetic wave. And so I'm gonna try to draw this picture a little bit bigger. You're trapped in this spherical cavity, or well, not really spherical, but it's a cavity that has a definite shape. Little hole here. And the idea is you analyze the wave as a set of standing waves. So again, we understand the electromagnetic waves and actually I forgot to mention it's a conductive cavity. This is made out of a conductor. So we understand electromagnetic waves in the conducting cavity to be standing waves. Since we know that conductors cannot have components electric field parallel to the surface. So there cannot be a parallel component of electric field parallel to the surface. You cannot have that because it's a conductor. And this is going back to our study of electromagnetic theory. All right. So what that means is that you must have standing waves. You must have a node at the walls. Okay, so there must be a node at the walls. So again, we understand electromagnetic waves in the conducting cavity standing waves, since we know that there cannot be a parallel component of an electric field parallel to the at the surface of a conductor. Okay, it can only be perpendicular. All right. So what that means is that there must be there must be nodes at the surface of the conductor. So the standing waves in the black body or the electromagnetic waves in the black body or in this cavity, the electromagnetic waves in the conducting cavity must have nodes at the walls. And so they are standing waves. It must have nodes at the walls because you cannot have a parallel component of an electric field in a conductor at a conducting surface. So as the theory goes, you can draw these, many electromagnetic waves that again are standing waves in a conductor. So again, they're all over the place. Many of them. They all form standing wave patterns at the conductor. So you derive this in a three-dimensional sense, and you find out that the result is nonsense. So again, we consider the electromagnetic waves as stationary or as a continuous, and we have no reason to think otherwise because of the great work done by Maxwell. So we perform an analysis. and calculate the radiant intensity. By integrating, again, using integral calculus, over these continuous electromagnetic standing waves. I'm underlining certain words for a reason. And we find a result that's nonsensical. For blackbody radiation, as it's called. And this experiment sets up a black body, right? What this is an experimental version of a black body with emissivity equal to 1. This is an experimental way of setting this up. And when you integrate over all of these continuous electromagnetic waves, you find an answer that is nonsense. Okay, it was so bad, they refer to it as the ultraviolet catastrophe. All right, so again, we perform an analysis over all, we try to calculate the radiant intensity by integrating over the continuous electromagnetic standing waves. We find a result that's nonsensical for black body radiation. Again, this is our version of a black body, but we're integrating over, again, integrating would be integral calculus because you're using what? Continuous electromagnetic standing waves. And when you do that, I mean, you go through this analysis, I've been through it many times, and it makes total sense if you're a 19th century mind. You haven't had quantum physics, it makes total sense. But the answer is nonsense, and people cannot figure that out. So again, this was worked out by, James Jeans and Lord Rayleigh. So this analysis was worked out by two great physicists, by James Jeans and Lord Rayleigh. Heard about Lord Rayleigh before? No, the Rayleigh's criterion for resolvability back in wave optics, chapter 27. That's the same Lord Rayleigh. The ridiculous theoretical analysis or nonsensical theoretical analysis, or the nonsensical and theoretical analysis was fine. It should work if you didn't think about things being, you didn't think about quantum physics. So the nonsensical results of their analysis, if I was teaching physics, modern physics, I'd go through the analysis. Gave, or what was called the ultraviolet catastrophe, or was deemed the ultraviolet catastrophe by people. They thought it was terrible. You can look up ultraviolet catastrophe. It's very real. That's how bad the results were. So when Lord Kelvin was giving his speech, you know, one of the things he was thinking about was the ultraviolet catastrophe. So again, this was worked out by Jeans and Rayleigh and got nowhere. All right, so the next person who essentially, I guess, has his turn in the barrel was a German physicist, Max Planck. All right, so the next person to attack this problem was the German physicist, Max Planck. Again, you heard about Planck's constant, so he must have done good things, right? So the next physicist after Rayleigh and Jeans to attack the blackbody problem was German physicist Max Planck. Max and then Planck is P-L-A-N-C-K, not P-L-A-N-K, as I see a lot of people write. He's not Max Planck, he's Max Planck. Okay, and so he's the next person, if you will, in the barrel. And he looked at the problem. And he also struggled. He went over all the work done by James Jeans and Lord Rayleigh. And again, he could get nowhere either. He could not find anything wrong with their work. So oftentimes, you know, when you're, let's say if you're, many of you out there are computer programmers, you know, and sometimes, you know, you look at something and you just get frustrated and can get nowhere. And what do you start doing? Well, you start trying things. So saying, well, let me try this, let me try that. Because all the other previous work wasn't panning out to anything. And so, again, you know, Max Planck lived from 1858 to 1977. Right. So, again, a little bit of Max Planck. He was a personal friend of Albert Einstein's. And Planck worked on relativity and quantum theory. All right, so again, so Max Planck was a friend of Albert Einstein. And he worked on relativity and quantum theory. Again, he is some people refer to him as the father of quantum mechanics. In fact, Planck, in 1906, Planck wrote a paper Planck wrote a paper giving the correct relativist expression for momentum. Remember, that's gamma mv. That relationship, that relativistic momentum, is due to a 1906 paper by Max Planck. Again, we talked about the 1905 papers by the great Albert Einstein. 1906, Planck worked to enhance Einstein's relativity theory by giving the correct relativistic momentum. So momentum we studied was something that was worked up by Max Planck. So what did Max Planck do here? Well, again, he had, he struggled like everybody else did. But one of the things he tried, he says, well, I don't know. What do we consider these oscillators to be quantized? Let's say instead of the light being in terms of continuous electromagnetic waves, let's think of them as quantized particles again. Yes, I know that seems like we're taking a step back. And we had, we just 30 years earlier, we had the great electromagnetic theory, the great amalgamation by Maxwell. But let's consider here that we consider these, so the light as quantized to see if it works. So Planck tried a solution by assuming that light was composed of packets of energy. Given by E equals HF. All right, and so what he found then is that what he discovered is that in doing this, he added, not integrated, he added the discrete energies in the analysis to obtain the radiant intensity and totally match the true experimental blackbody curve. And we talked about this curve in physics 1. Okay, and so he was able to match that blackbody curve. If he considered light to be composed of packets of energy, which we now call photons, he was able to go through and do the same analysis, but this time he was adding discrete energies as opposed to integrating over continuous light, continuous waves, and he was able to perfectly match the blackbody curve. That's what he was able to do in this analysis. He's able to perfectly match the blackbody curve, but it required him to assume that light was composed of packets, of particles. All right. So remember the blackbody curve. If you recall, you had the radiant intensity versus, so you look at the radiant intensity. So for instance, I look at the radiant intensity versus wavelength. right? Do wavelength over here, and here's like we call the radiant intensity. I might have a curve like this, and again, I'm not remembering these temperatures very well. Like, let's say this curve would be for temperature T equals 1000 Kelvin. Okay, so peaks right at some temperature, or peaks at some wavelength. And if I consider curves for higher temperatures, we find out is that the peak of the wavelength shifts to the right, and the curve shifts up. This might be for, let's say, I'm not drawing these beautifully, 1500 Kelvin. And I might have another curve again that shifts. This might be, let's say, T equals 3000 Kelvin. I get curves that, again, they peak. The peak of the curve is at a wavelength. The wavelength, as the temperature of the black body increases, the wavelength where the peak occurs shifts to the left, gets smaller and smaller, and the peak intensity gets greater. Max Planck was able to show this. Again, this is the radiant intensity. And this is the spectrum. This is the spectrum of electromagnetic waves. And we see the intensity is greatest for a particular wavelength, but that wavelength shifts as the temperature gets higher and higher. Planck was able to reproduce this perfectly, provided that we accept light as being composed of tiny particles or packets of energy that today we call photons. So Planck, in his analysis, Planck was able to reproduce, by considering light as composed of discrete packets of energy, discrete as opposed to continuous. Planck was able to accurately or precisely reproduce the black body curves as shown above. We'll say the spectral, because it's over different wavelengths. Radiant intensity curves for black body radiation. Okay. He also required that only certain allowed energies of light can actually exist in the cavity. So what this goes, so considering light as composed of these discrete energies, essentially Planck also deduced that the energy of any oscillator, if you will, the energy of any oscillator, any electromagnetic oscillator, found in the conducting cavity can only have allowed energies given by, we call it E sub n, if you will, is n plus 1/2 times HF. Where H is a fundamental constant universe. It's equal to 6.626 times 10 to the negative 34 joules second. A fundamental universal constant called Planck's constant. So the fundamental constant of the universe called Planck's constant. All right, and so this is fundamental importance, that the only energies in this cavity that can possibly be true of any oscillator, of any electromagnetic wave that is standing, a standing wave in this cavity, the only allowed energies are given by n plus 1/2 times HF. F is the frequency of the light. Okay, so again, n is a number. So n can equal 0, 1, 2, 3, ... F is the frequency of light. And remember, for electromagnetic waves, C equals lambda F. So the wavelength and the frequency are related to each other by the speed of light. The only allowed energies of the oscillators that comprise the waves trapped in the conducting cavity come in the form of the quantity n plus 1/2 times HF. H again is Planck's constant. It's 6.626 times 10 to the negative 34 joule seconds. Why do we know it's joule seconds? Well, this is joules and the frequency is 1/second. So you multiply both sides by second, you get the Planck's constant must be in terms of joule second. Okay, that is the fundamental constant of the universe. What else does this tell you? Well, it tells you that what the difference is between each of these energy levels. So you look at the oscillator energy levels, you can draw, what's called an energy level diagram. And this is a diagram that's typically used in quantum physics. We call it the energy level diagram. So you draw an energy level diagram of this. So energy level diagram of allowed energies of oscillators, of electromagnetic oscillators bound in the conducting cavity. What do they, what's it look like graphically? Or we'll say black body cavity. A lot of adjectives here. Well, I told you what it looks like, right? It's E sub n. It's n plus 1/2 times HF. That means if I were to, again, energy level diagram, what it is it's just all the allowed energies that are that can happen. So again, they're in equal amounts. So this is again, these are all in fractions of HF. Right? So we're multiplying by anything here by HF. This would be, if n equals 0, this would be 1/2 hf. This would be adding, the next one would be 3/2 hf. Next one would be 5/2 hf. And then 7/2 hf. And all the oscillator frequencies are all related like this. You can go on and on forever. There, you cannot get, 0.45 hf or 1.389 hf. Those are not allowed energies. The only energies that are allowed are this discrete energies. No other energy is allowed in your system. No other energy of an oscillator cannot be anything other than what is prescribed by this formula. The difference between any two levels, if I take delta E, the difference between these are called energy levels, right? So E sub n defines energy levels. So E sub n defines quantized energy levels. For we'll say, I've already told you what we're studying here in the cavity. Okay, the difference between any two energy levels is delta E. So the difference between any two energy levels, or between two consecutive energy levels, is delta E, which is HF. So I don't care if I do n equals 5 and n equals 4, whatever, or 3 and 2, or whatever it is. Any two consecutive energy levels, they differ by an amount HF. All right. So again, this is something we have no direct experience in our macroscopic existence. The energy is quantized. Okay, this is new for us. Okay, we can understand the quantization of mass. We can understand the quantization of electric charge. But what Plunk determined is that if he is going to correctly describe the radiant intensity, and hence the power, equals sigma EA T to the fourth, if he's going to describe that for radiation heat transfer, you must consider light not as a continuous electromagnetic wave, but you must consider it as a packet of energy, a particle. Today we refer to this particle as a photon, but the light that is inside, the electromagnetic waves that are inside of the cavity, of the blackbody cavity, the conducting cavity. To do this analysis appropriately, you must consider the way that the cavity consists of light as discrete packets of energy and not electromagnetic waves. Now, this is very weird, and it flies in the face of what the physics community believe. In fact, Planck almost didn't want to even publish because, in physics, yeah, everybody can be wrong and it's okay to be wrong. But at some point, there's a level of wrong that's acceptable. You don't want to put yourself out there to be a crackpot or just massively inept. You don't want to have yourself look like that. So again, Max so only 30 years earlier, Maxwell showed that light was definitely a wave with the publication of electromagnetic theory. Okay, so Planck was reticent. So Planck at first was reticent to publish. Because he needed light to be particles again. To correctly describe blackbody radiation. You know, his 21-year-old friend named Albert Einstein actually was very convincing of Planck to, you know, he encouraged Planck to publish. So 21-year-old Albert Einstein his friend Einstein encouraged Planck to publish. And, you know, Planck received the 1918 Nobel Prize in Physics. For this work. So, and he's been deemed, you know, the father of quantum mechanics by many people, right? So again, the issue that Planck had was you have to try to take new ideas and convince the 19th century mind, even though we're barely in the 20th century. Planck did this in 1900. All right, so this is so again, this is in 1900. I forgot to mention that. It's kind of funny how I tell you modern physics is the physics from the 20th century onward. Well, literally, this very result happened right at the year 1900. 1899, you have Kelvin saying we got it all figured out, and here in 1900, well, I don't know. Light seems to be a particle. And, you know, and again, Planck was you know, worried about this, and we'll find out that Albert Einstein, one of his papers was a photoelectric effect, and he showed, yea, verily, that light actually indeed is a particle. All right, and so now let's take a look at how big HF is. All right, and so, you know, is this big enough to even worry about? So let's, for instance, let's consider infrared radiation like you would have in the blackbody cavity. And how big is HF? So let's say for instance, consider, so doing this, we consider F to be about, let's just say 10 to the 14th hertz is a good frequency in this range. How big is HF? Well, HF will be Planck's constant, 6.626 times 10 to the negative 34 joule seconds times 10 to the 14th hertz. So again, a sample energy. We find out that delta E, if I calculate this out, delta E becomes about 6.63 times 10 to the negative 20 joules. And again, if you convert this to something that's more useful, like electron volts, we have an electron volt has 1.60 times 10 to the negative 19 joules. We find out that delta E for such, say a typical cavity where you'd have about, say, 10 to the 14th hertz or so, delta E is going to be on the order of 0.4 electron volts. Well, that is significant. All right, so this is significant. Since we'll find that typical atomic energy is on the order of an electron volt. And thermal energies are on the order of a fraction of electron volt. So we're right there. These are significant energies. Okay, so again, the difference in energy between, let's say, one energy level in the among the oscillators in the cavity radiator, or the blackbody cavity radiator, and another is on the order of about 0.4 electron volts for a typical IR energy, or typical IR photon, we call it. So I mean, again, typically in the IR, it's a good frequency to consider, 10 to the 14th hertz. So this is on the order of atomic energies. So again, this is something of importance. All right. So what's interesting here is that we're seeing a result that clearly looks like it's macroscopic. Thermal radiant intensity, but it comes from a microscopic source. All right. So again, this is a typical situation of the effects of quantum mechanics. All right. And so we see that even if macroscopic energies are quantized, or even if macroscopic energies are quantized, you know, what we see, the quantum steps are too small to be noticed. And again, this is another example of the correspondence principle. You know, this is another example of what's called the correspondence principle. That macroscopic quantities inevitably depend on quantum mechanical phenomena. So typically, the work done by Plunk and the concept of the ultraviolet catastrophe, and you know the issue of studying the blackbody radiator, cavity radiator, is oftentimes considered the fundamental seeds of quantum mechanics. So, you know, what actually started quantum mechanics. But we saw examples and evidence of things that we could not explain in other forms. So one of the things that we see is if you were to look at gases, you put say a current through a gas, and it's going to emit or absorb energy. Well, it only does so. We find out that it only does so in discrete lines. We'll talk about what's called a line spectrum. Okay, so again, this is evidence leading to a need for quantum mechanics, and in fact, quantum results. But we can go further back than this. So let me share my screen here. We can go back and talk about what are called a line spectra. Let me show you a picture of this. So I'm just going back to the OpenStax textbook. And we can see that, I mean, what are we looking at here? Well, we're seeing is we're looking at, for instance, an energized gas. All right, so there's electromagnetic there's a current going through a gas, and there's an emitting electromagnetic spectrum. But you'll notice that not all waves are actually emitted. Only certain lines are actually emitted in the spectrum. The spectra is actually, in fact, we understand this so well that we actually can look at these spectral lines form a signature. And we understand the signature so well that we can actually identify what the gas is by just looking at its line spectrum. All right, and so we can look at, for instance, if we pass a current through a gas, and say cathode ray tube, and I'll talk more about these in a moment, but these are the typical, you're passing a current through a gas from what I'll say the cathode to the anode, from one side of a chamber to another. You have so you pass a current through in a cathode ray tube. filled with gas, filled with a gas, it only emits certain, or only emits or absorbs certain discrete wavelengths. Forming what is called a line spectra. Okay. So in fact, this spectra, this line spectra, can be used. I mean, becomes a is a signature to help identify an unknown gas. So, for instance, you can look at a star like the sun and understand what it's composed of. So we can look at a star. Look at the sun or a star. And understand its composition from the line spectrum. But what causes this line spectrum? Again, this was done by spectroscopists for years, but nobody understood what it was. Now we're going to study this in a little bit, more in chapter 30 than here. But again, as it turns out, we'll find that the atoms and molecules composing a gas have electrons that can only exist at certain quantized energy levels. All right, so when they transition from one level to another, they either absorb or emit a photon of a specific frequency. All right, so they're only at certain energy levels. So you might say, well, I have an atom here. Say I have, a positive, nucleus, and the atom. Now again, we're going to kind of draw a real basic planetary model of the atom for the moment. But the atom can only exist at certain energy levels. Or the electrons. So this is the nucleus. See, put a big plus there for positive. And you got an electron sitting here, or maybe electrons sitting down here. and they can only have a certain energy. In order to go from one to the other, they will make a quantum jump from one energy level to another. When they do so, they either, like this one here is in a higher energy level. So if it wants to jump to a lower energy level, it gives off a photon. So it gives off a photon where the frequency, the change in energy of this photon is going to be delta E equals HF. Or we know that C equals lambda F for any wave. So instead of writing F, I can actually write C over lambda. Okay, and so I can actually write that this change energy is HC over lambda. So what I actually see is that there's only allowed energy levels in a particular atom. And so when you have let's say an electron going from higher energy to a lower energy, it's going to give off a photon. Photons can only have wavelengths or frequencies that correspond to the particular change in energy for that particular atom or molecule. If you want to go from a lower level to a higher level, you must absorb a photon to give you the energy to propel you to do that. Again, we find out later on, we haven't talked about this yet, but we find out later on that in order to understand line spectra, we must have quantum mechanics. The whole concept, the study of line spectra is called spectroscopy. It's been around for 100 years prior to quantum mechanics. All right, so the study of line spectra is called spectroscopy. We have spectroscopists now. We use it in astronomy. So study of line spectra is called spectroscopy. And it predates quantum mechanics by many decades. Again, another example of using something you understand experimentally before the theory comes along. And we saw this electromagnetic theory too. We saw the telegraph. You know, we were fully using electromagnetic theory prior to having an understanding of what it actually was with the telegraph. So again, this predates quantum mechanics by a lot. This is one of those things that, well, you know, we understand it. We're able to identify for some reason, you know, the gases that compose a star, but we have no idea of what is going on in the physics here, but we still used it. So again, another unanswered question at the turn of the century. Did not understand, you know, what, you know, how this line spectra works. Okay, so again, we go on to our next development of quantum mechanics. We had Max Planck in 1900 with blackbody radiation, and he was able to get the correct blackbody radiant intensity curve, and hence understand or derive the power law for radiation heat transfer. You know, that P equals sigma E A T to the fourth that we studied back in physics 1. But he required light to be composed of packets of energy, discrete packets of energy, and not a wave. It seems like we're going backwards to some extent. Here we had the big fight over what is light. Is it a particle or a wave? Now we find out, well, yeah, verily it's a wave, no doubt about that. That's what Maxwell showed us. And all of a sudden now we're retracting, it seems, because now we're seeing like, well, I mean, if I assume it's a particle where the energy is given by HF, and the oscillator frequency, you know, again, for the oscillators, n plus 1/2 that's going to HF, well, then I'm able to correctly and precisely describe radiation heat transfer. So what is it? Is light a wave or is it a particle? All right, so we're going to get into that here in this chapter. So the next person to step up to the plate was Albert Einstein. Again, he did that in 1905 in the Anna Mirabilis. Okay, so again, Planck's work is done in 1900. Right? So Planck did his work, nicely right at the turn of the century, 1900. The next person to step up is Albert Einstein. So Albert Einstein in 1905, Albert Einstein or one of the four seminal papers published by Einstein was on the photoelectric effect. In fact, of all the things this great man did, what he won the Nobel Prize for was not relativity, it was the photoelectric effect. All right, so Einstein won the 1921 Nobel Prize for the photoelectric effect, for his work on the photoelectric effect. So this basically this paper. All right, so what is the photoelectric effect? Well, quite simply, it is light particles, photons, knocking out electrons. And those loose electrons form a current and form electricity. Photo means light, electric, again, electricity. So long and short of it is, in a simple way, when light strikes materials, it can eject electrons from them. Okay, so essentially what this means is that this is called the photoelectric effect. From photo, which means light, creating electricity. All right, so your light is knocking out electrons from materials and generating electricity because now you have loose electrons floating around. All right, and so we see the photoelectric effect in many places, actually. It's not too foreign. We use it in many ways. Okay, so we see photoelectric effects in say light meters. So the photoelectric effect is used in light meters, such as the ones that adjust the automatic iris on many types of cameras. All right, so photoelectric effect is used in light meters. All right, such as those that adjust the automatic iris in various types of cameras. Okay, so we use the photoelectric effect for that. We also see the photoelectric effect used in, like, let's say, in photocells, like on your calculator, or when you're looking at solar cells, let's say on the roof of a building, or on certain objects that like I've seen signal lights run off solar cells. My automatic gate in my house has a solar cell that provides power to it, right? And so a lot of the solar cells operate via the photoelectric effect. Okay, so it's very important to our society. And this is seen on your calculator. Roadside signs. What else? Solar cells on a roof. Or operating signal lights. Etc. Right. So you see this technology in many places. All right. Now, so we've known about the photoelectric effect for more than a century. All right. So long and short of it is, we have known about the photoelectric effect more than a century. It's nothing too new. Okay, so why is it so important here? So let me share my screen to kind of give you an idea. Albert Einstein, what setup did he do to make this work? So I'm going to go and share my screen again, and I drew up in PowerPoint what the photoelectric experiment may very well look like. So let me share my screen. I'm going to talk through it at first. So when I talk about, so what I'm going to talk about here is I have an evacuated chamber. So right here is an evacuated chamber. No, it's a vacuum inside here. Inside here are two metal plates. We'll call this one the anode and this one the cathode. Okay, there's basically two metal plates. Now, what happens is that this is a light source. Light, which we understand what Einstein is going to show you is composed of photons or particles of light. Oftentimes, the symbol of light is you look at it and you give it a wavy line with an arrow. That's typically your symbol for light. So photons will strike the anode. They strike the metal plate. When they strike the metal plate, they eject electrons through the photoelectric effect. Now, there is a circuit that's attached to this. And so what's happening is you're sending, so plates, these electrons are going to go across this evacuated tube to the cathode. And what you're going to see is you're going to see a current developing in the attached circuit. Now notice at the bottom of it is a battery that's actually an opposite polarity to the current. All right, so notice that the long side of the battery, the positive side, is directed that it would actually create an anti-current, or a current that would actually oppose the current that's being the photoelectric current. And the idea is we want to figure out how much energy these ejected electrons have. And how do you do that? Well, you set up a potential in the battery, epsilon, such that you figure out what potential you need to just stop this current. You figure out the potential that you need to just stop the current, and you know that the current is composed of electrons. Electrons have a certain charge Q. There's a certain potential V, which would be, or epsilon or potential V. That is the energy of these electrons, and hence the energy of the photons that ejected the electrons. The idea is that a photon is going to eject an electron. Now, an electron may have any energy from 0 all the way to the energy equal to the photon. If the photon was successful in literally converting all of its energy to the electron's kinetic energy, then you would see that would be the maximum kinetic energy possible for the electron. Any other smaller energy, any other energy would be smaller. You would have a partial conversion from the photon energy to the electron energy. And so when you have the stopping potential, you are going to stop the fastest electrons, i.e., the ones that are where all the photons energy was converted to the electrons kinetic energy. And hence, if you stop those, you stop any of the ones that are slower. All right, and so you're finding what's called the stopping potential. All right, and so we're trying to figure out is well, let me write this out. So let me stop sharing my screen. And let's talk about what we just saw. I'll try to depict this in a way that's on the, my drawing skills. So what did we just see? Well, we see an anode and a cathode, basically a fancy name for two metal plates. All right, and they're in an evacuated chamber. All right, again, this is the anode. This is the cathode. Okay, now light from some light source will strike the anode. These are photons coming out of the light source. Electrons get ejected. And they will go across the evacuated chamber. Try to draw this a little bit better. So these are little electrons going this way. Another one. Let's draw a third one. There's many of them. Right? Okay, and then This is an evacuated chamber. Or evacuated, I wouldn't say a chamber, it's evacuated, say, tube or some sort. It's called a cathode ray tube, right? Inside here, we have a circuit hooked up. But the battery is set up in the reverse polarity. So these electrons that get ejected are all going to come down here, and we'll say there's a current. All right. So again, the idea is, I'll call this. Okay. What's happening? Photons from the light source eject electrons from the material, from the anode material, whatever the anode's made out of. It's some material from the anode material. And anodes are made out of different things. Okay, that's the first thing. Okay, the electrons accelerate from the anode to the cathode. And create current I. In the attached circuit. Okay. Now, in each process of the collision, when a photon collides with an electron, it yields a percentage, some varying percentage of its energy to the electron's kinetic energy. Or we'll say varying fraction. The maximum kinetic energy of an electron is for ones in which the photons, now again, the understanding here is all photons are identical. With frequency F, and energy HF. And this is what Einstein was thinking about. All right, so all these identical photons are striking electrons, and they're giving the electron, depending upon the collision, they're giving the electrons a different amount, a different fraction of their energy to the electron's kinetic energy. Now, if in a certain situation, the collision was just right, where all of the photon's energy was converted to the electron's kinetic energy, then the electron would experience its maximum kinetic energy. Okay, so again, so the collisions are all different. You have a variation of the collisions. So in some cases, the photon gives all of its energy to an electron's kinetic energy. Which gives the maximum kinetic energy of an electron, which yields electrons with maximum kinetic energy. All right, so there we are. Now, one more thing. We will now try to figure out what this maximum kinetic energy is by doing what we're going to. We have a voltage source that has opposite polarity, and we're going to figure out what voltage source creates zero current. We want to oppose it, and when we balance out that current, we find out what's called the stopping potential. So we're going to do is we're going to now. We now. I'll just write it out. We now apply a voltage source in the current. Oh, sorry, in the circuit. With opposite polarity. To the photoelectric current. Okay. The potential to create an opposing current and stop the photoelectric current is called the stopping potential. All right, what you've done when you create the stopping potential, we can use the stopping potential to figure out the kinetic energy of the maximum kinetic energy of the electrons. All right, and so we can use the stopping potential to measure the maximum kinetic energy of the electrons. With photoelectrons. We'll call that Ke sub E. Okay, that would be the maximum kinetic energy of the photoelectrons. And how do we know that? Well, that's because the maximum kinetic energy of the photoelectrons will be exactly equivalent to this Q V stop. Or we can actually say Q sub E V stop. Because we know how much charge an electron has. All right, so once we know, again, a charge going across the potential difference, again, that is the, we call that the potential energy. So we have the stopping potential energy equal to the kinetic energy. That allows us to measure the maximum kinetic energy of the photoelectrons. Okay, so we have an understanding then that, so Einstein understood that an energy was required, that there was also an energy required to remove the electron from the material in the first place. This is called the binding energy. As we just call it BE. And some people call it the work function. All right, so the idea is that, well, there's a certain amount of energy from the photon. Okay? Given that energy from the photon, it's going to need a certain amount of binding energy to be able to eject the photoelectron. Any kinetic energy that you measure after that is additional. So what this really means is that when you look at the energy from a photon, HF. Well, energy of the photon has to be equivalent to the binding energy to actually break the electron away in the first place. Then, if the photon energy is just equal to the binding energy, you're going to break an electron away that's not going to have any kinetic energy. So any kinetic energy that you measure is above and beyond the binding energy, right? So you have this relationship that the total energy from a photon, HF, is the binding energy, the energy you need to break the electron away in the first place, plus whatever additional kinetic energy. So generally speaking, what Einstein wrote is that he determined that the maximum kinetic energy that we're measuring with the stopping potential is really the photon energy HF minus the binding energy of the material. Every material has a different binding energy. All right, so let's look at the findings from Einstein's experiment. Again, Einstein wrote this paper. Unlike a lot of his papers are very much theoretical. This paper has a very strong experimental flair to it. Okay, so what did Einstein find out? First of all, Einstein looked at this experiment, and he interpreted very correctly and very deeply the meaning of how this experiment showed that light consists of particles called photons. I mean, that's what this experiment showed Einstein. How did he see it? So again, Einstein's interpretation of the photoelectric effect. All right, so we're going to kind of compare what you should see if light is composed of particles, and then what you would see if it was actually a wave. All right, so one of the first things, number one, Einstein saw that if we vary the frequency of the electromagnetic wave, radiation, if we vary the frequency of the, I'm going to use EM for electromagnetic, of the electromagnetic radiation, okay, we vary the frequency of electromagnetic radiation falling on the material. Okay, we find the following. All right, so first of all, for a given material, there is a threshold frequency F naught. So threshold frequency F naught. For electromagnetic radiation below which no electrons are ejected, regardless of intensity. So again, it doesn't matter the intensity. Unless I achieve a certain minimum frequency F naught, no electrons are ejected. And it doesn't matter if it could be highly intense. It could be like a laser. I'm not going to inject electrons unless I have a minimum frequency. Okay? You're not going to inject electrons unless there is a minimum frequency. lest you achieve a minimum frequency, irrespective of the intensity. All right. Now, essentially, what this means is that if the energy is too small, so again, what interpretation does this take? Well, if light is a particle, if it's energy, it needs at least energy, minimum energy, E sub min equal to HF naught to break the electron away. From the atom. Any less energy is not going to do the job. The energy is HF. H is a constant. If you do not get the minimum, to get the minimum energy, you need a minimum frequency. Any frequency that's smaller than that is not going to do the job. Okay. Now, if light was a simple wave, sufficient energy could be obtained by just increasing the intensity. Right. So again, if light was a wave, light was a simple wave, sufficient energy can be obtained by with this. So the sufficient energy could be obtained with the sufficient intensity. Because the wave, the intensity is the amplitude squared. But as Einstein found out, that intensity doesn't matter. If light was a simple wave, all you'd have to do, you could beat this by just having the wave be intense enough. But as Einstein showed, intensity does not matter. The only way you're going to have a minimum frequency, F naught. If light doesn't attain at least this frequency, no electrons will be ejected. This backs up light being a particle and definitely not a wave. Let's look at finding number 2. And these are all things that Einstein saw and made the correct interpretation. Finding number 2. Once electromagnetic radiation falls on a material, electrons are ejected without delay. So once electromagnetic radiation falls on a material, the electrons are ejected. Without delay. They're instantaneously ejected. They're immediately ejected. No delay required. Okay. Now, again, if light's an individual photon, all you have to do is have a sufficiently high frequency, and you start breaking electrons away from the material. For if electromagnetic wave if EM radiation is a simple wave, we'd have to wait several minutes for there to be enough energy to deposit on the metal surface to start ejecting an electron. All right, and so again, this is another result that points at light being sort of particles. So again, in the to support the particle theory, basically as soon as individual photon has sufficient high frequency, so as soon as an individual photon has sufficiently high frequency, it can eject an electron. It can immediately eject an electron. There's no waiting. It can immediately happen. And immediately happen right off the bat. On the other hand, if it's a wave, what's the case? Well, if the electromagnetic radiation is a wave, is a simple wave, so electromagnetic radiation is a simple wave, several minutes would require for sufficient energy to be deposited on the metal surface to eject the electron. All right, so several minutes would be required for sufficient energy to be deposited on the material to eject an electron. Okay. So again, once the electromagnetic radiation falls on the material, electrons are ejected without delay. That means they get ejected immediately. There is no delay in the ejection. There's no waiting. Now, again, with the particle view of light, being a photon, as long as it has sufficiently high frequency, it can immediately eject an electron. On the other hand, if the electromagnetic radiation is a simple wave, you need to wait several minutes for there to be sufficient energy deposited on the material to start ejecting electrons. So there is a wait if the electromagnetic radiation is a wave. So again, another finding that points at light being composed of photons. Okay, let's look at finding number 3. So finding 3 says number of electrons ejected per unit time is proportional to the intensity of electromagnetic radiation and to no other characteristic. All right, so the number of electrons. Number of electrons, let me see here. Ejected per unit time. Okay, is proportional to the intensity of electromagnetic radiation. And to no other characteristic. All right, so let's look at that. So again, the number of electrons ejected per unit time is proportional to the intensity of electromagnetic radiation and to no other characteristic. All right. So essentially what this means is that high intensity electromagnetic radiation consists of large numbers of photons per unit area. And all the photons have the same energy HF. So the idea is, high intensity electromagnetic radiation is just going to be composed of just a lot more photons, but they're all identical. HF, you just have more photons per unit area. So what are you going to do? You're going to eject more electrons. But that's it. So again, looking at this as high intensity electromagnetic radiation consists of large numbers of photons per unit area. That's all it is. Want more intensity? You just have more photons per unit area. So a larger number of photons per unit area with all photons having the same characteristic energy HF. All right, so again, high intensity, all it means in this experiment is that you just have many more photons per unit area than you had before. Higher the intensity, the more photons per unit area. All the photons are identical. If the frequency is F, every single photon is an identical twin. They all have energy HF. And you just have more of them per unit area. That's it. Now, the fourth finding by Einstein kind of goes along what we were talking about earlier. So number 4, the fourth finding of Einstein is we can vary the intensity of electromagnetic radiation. And measure the energy of the ejected electrons. And we find the following. The maximum kinetic energy of ejected electrons is independent of the intensity of the electromagnetic radiation. All right, so the maximum kinetic energy. We did the whole thing with the stopping potential. The maximum kinetic energy of ejected electrons is independent of the intensity of the electromagnetic radiation, or so independent of the intensity of the electromagnetic radiation. This goes about what we talked about the operation of the experiment. It really only depends on HF. It depends on the energy of the photons. The energy of the photons are going to be what the photon energy is going to be what knocks out an electron. All right, and so again, you're only going to because there's so many electrons in the material, it's highly unlikely that two photons will strike the same electron simultaneously. Again, the maximum kinetic energy that'll never happen. You're only going to get one photon colliding with one electron. All right, and so again, this gets into why number 4, and let's kind of continue why number 4. Well, the rationale is, since there's so many electrons in a material, it is highly unlikely that two photons will interact with the same electron at the same time. First and foremost, you're not going to have it's going to be a one-to-one interaction. So you're not going to have two photons contributing all of their energy to an electron. That's just not going to happen. At best, you're going to have one photon colliding with one electron. So the maximum kinetic energy would be one photon giving all of its energy to contribute to the kinetic energy of a single electron. Okay, you're not going to have this. You're not going to have a pairing up of photons, for instance. All right. So now the maximum, as I stated before, the maximum kinetic energy of an electron is the case where the photon gives all of its energy to the binding energy to break the electron away plus the electron's kinetic energy. And that's the best case scenario. All right. If the electromagnetic radiation is a simple wave, the higher intensity could give more energy, and higher energy electrons could be ejected. All right. And so again, if we're talking about a simple wave, you can make energies of any level, if you wish, by just increasing the intensity. All right. So again, we're looking at a model of the photon of light being composed of particles. So if, again, continuing with number 4, if the electromagnetic radiation was just a simple wave, okay, if it was a simple wave, a higher intensity could give more energy. And you can have higher energy, higher kinetic energy of electrons. So it could give more energy to provide higher kinetic energy of ejected electrons. Again, we're not seeing this. Intensity doesn't matter. So again, we're seeing over and over again that light must be a particle for these observations to be true. Okay, so again, we'll just call them electrons. Call them photoelectrons. We'll just call them electrons. Okay, so again, that's observation number 4. And observation number 5 is essentially that equation I gave. So Einstein was able to put everything together and give a relationship. All right, and so Einstein was able to show you that the maximum, again, understand this formula you get out of the photoelectric effect experiment. Ke sub E is HF minus BE. Again, this is the maximum kinetic energy of ejected electrons in the photoelectric effect. BE is the binding energy. Or what we might refer to as a work function. Okay. This HF is the energy of the photons. In the incident electromagnetic radiation. All right. Now Einstein provided a nice graph of this relationship, and so we see. So let me show you the graph now. So Einstein's graph is the graph of the maximum kinetic energy. Again, this is what he measured with the, by understanding what is a stopping potential. The fundamental charge on stopping potential is the maximum kinetic energy. So he measured, or he basically graphed the maximum kinetic energy, Ke sub e, versus the frequency f. And he found out that the line looks like this. A nice straight line. This is F naught. The minimum energy, the minimum frequency, and that's when the frequency of light exactly equals the work function with no kinetic energy left over. Literally, the frequency of the binding energy is equal to this minimum frequency of light, where the frequency is just enough to break the electron away from the atom, but not enough to give it any kind of kinetic energy. So again, this occurs when HF naught occurs when it's just enough to equal the binding energy. So this F naught would just be the binding energy, Be, divided by Planck's constant. So I can label it Be, binding energy. That is the fundamental energy. How much energy is required to remove the electron from this atom or molecule? Divided by H. And this curve, what is this curve representing? This curve is representing this equation right here. Ke sub e is HF minus binding energy. Okay, so when Ke sub e is 0, then HF equals the binding energy. You get this particular situation. No frequency less than F naught will eject any kind of electrons at all. Okay, so this, again, every collision between a photon and an electron, the photon will give a fraction of its kinetic energy, or a fraction of its energy to the kinetic energy of the electron. So it's going to be anything from no energy at all the way up to everything. Okay, so again, that is, but if you have a frequency, if you have an F that's less than F naught, you don't get any ejected electrons at all. And this is what Einstein found. Now, what's the takeaway, or the great takeaway from Einstein's photoelectric effect experiment? All right, so let's kind of understand what we should take away from this experiment. Why was this experiment so crucial? Why was this experiment so important? Okay, Einstein's idea electromagnetic radiation is quantized was crucial to the beginnings of quantum mechanics. All right, so again, Einstein's idea that electromagnetic radiation is quantized. So that's crucial to the beginnings of quantum mechanics. so it's quantization of energy. And again, it's far more general than the photoelectric effect might apply. Essentially the idea is that the electromagnetic radiation can be modeled in the form of photons, and the characteristics of electromagnetic radiation are entirely consistent with this fact. All right, and so again, Einstein, Einstein's idea was different than, say, Planck's. In Planck's, well, it's not so different, but Einstein's findings look similar to Planck's findings. But Planck found, recall, Planck found that the difference in energy levels, the difference in the oscillator energy levels, that the difference in quantized energy levels of the bound electromagnetic oscillators bound in the conducting blackbody cavity was delta E equals HF. Okay, that's what Planck found. Planck found that, well, I have this blackbody cavity, this made out of a conductor, and I expect there to be standing waves. I expect that the electromagnetic waves will form standing waves in the cavity, because again, there cannot be any parallel electric field component in the surface of a conductor. And so there should be nodes at the walls of the cavity. And I should have standing waves. Well, Planck needed to employ the concept of quantized energy in order to be able to get the correct blackbody radiant intensity curve. And he finds that the difference in these energy levels is given by HF. Einstein is much deeper than that. Einstein found that the actual light itself must be packets of energy given by HF. All right, so Einstein went significantly deeper. So Einstein found that light itself or say found from the photoelectric effect that light itself is quantized. In packets of energy. given by HF. Okay, so light itself is quantized. This is what Einstein discovered. Light itself is quantized. All right, now this concept of light acting as a particle makes sense if you look at the behavior of higher frequency electromagnetic radiation. So, so again, if you look at it, electromagnetic radiation can be modeled in the form of photons. So electromagnetic radiation can be modeled in the form of photons. Okay, that's what Einstein predicts, and the characteristic of electromagnetic radiation is entirely consistent with this fact. For instance, the hazards of ultraviolet radiation and X-rays and gamma rays can be explained by light acting as packets of energy. So the hazards of high energy ultraviolet, X-rays, and gamma rays are consistent with light acting as packets of energy. Okay, so, and again, as I said, it was this work that got Albert Einstein the Nobel Prize. All right, so he got the Nobel Prize in 1921 for this very work, even though his greatest work was relativity. Okay, so let's do a few problems here regarding the photoelectric effect. All right, let's look at OpenStax 29.1. Again, we're still totally in alignment between the chapter number of Cutnell Johnson and the chapter number that I rely on for OpenStax. So again, let's look at OpenStax 29.1. Okay, what does this say? A lithium bromide molecule oscillates with a frequency of 1.7 times 10 to the 13th hertz. A. What is the difference in energy in electron volts between allowed oscillator states? So what is the difference in energy in electron volts of different between allowed oscillator states? And oscillator should give you a hint here. B, what is the approximate value of N? Okay, let's see here. For a state having an energy of 1.0 electron volts. Okay, read this again. So, a lithium bromide molecule oscillates with a frequency of 1.7 times 10 to the 13th hertz. A, what is the difference in energy in electron volts between allowed oscillator states? B, what is the approximate value of N for the state having an energy of 1.0 electron volts? All right, so not very big energy. All right, so again, we're talking about an oscillator, so we need to go back to the work done by Plunk. All right, so let's remember this. I'm going to erase it for real estate purposes. Okay, look at part A. What did Max Planck say for oscillators? So again, we're looking at oscillator energies. And we're talking about the quantum oscillator. So energies for a quantum oscillator. Like the electromagnetic oscillators bound in the blackbody cavity. Okay, so let's look at this. So, all right, so what will those energies be? We know them to be E sub n is n plus 1/2 times HF. All right, that's what they are. Now, we know the difference of these energies. So the difference is part A is asking us, what's the difference of these energies? Well, we know that Planck told us the difference of these energies is simply HF, right? If I go from n equals 2 to n equals 1, the difference of the two are going to be HF. Let's say like 3/2 minus 1/2 is 1. So difference is HF. So what would this be? Well, it'd be the difference of H being 6.626 times 10 to the negative 34 joules seconds times, what's the frequency? It was 1.7 times 10 to the 13th hertz. I come to find out that the energy between these two, any two oscillator states, I should say any two consecutive oscillator states, will be, okay, again, I got one more conversion. So we get it 1.13 times 10 to the negative 20th joules. We want this in electron volts. So one more conversion to do. We know that an electron volt has 1.60 times 10 to the negative 19 joules. So we find that the energy difference between any two oscillator states will be 0.071 electron volts. So quite small for this lithium bromide atom, or sorry, molecule. Now the question is, well, if you have an energy level that's 1 electron volt, what does that correspond to as far as what energy level is that? We want to solve for n. All right, so part B now says, well, we know what the energy is. Let's remember part A. We'll put part A in the parking lot. Okay, so stick part A in the parking lot. And that is that the difference between any two levels is delta E is 0.071 electron volts. Now, let's figure out, well, every energy level is different, right? So my lowest energy level, I mean, that's my HF. So 1/2 HF, half of that would be my first energy level. And then 3/2 would be the next one, 5/2 next one, and so on and so forth. That's how oscillators work, right? So if, as I go and increase in energy levels, I go to higher and higher and higher energy levels. At what level would I be at 1.0 electron volts? All right. So again, if I look at this, I know from this relationship that HF is 0.071 electron volts. This problem is saying, okay, you draw your energy level diagram. Okay, this is your energy. And let's say the energy we can express in terms of HF. And it's multiplied by this, right? And so the lowest one would be 1/2 HF. Say this is energy. The next one, 3/2 HF. Next one, 5/2 HF, and so on and so forth. And so I'm building up and building up and building up. What energy level would be 1.0 electron volts? That's what this problem is asking. How high do I have to go before I get to 1.0? All right. So how do you figure that out? Well, you set E. So again, you have E in oscillators is equal to the quantity N plus 1/2 HF. We're going to set E to 1 electron volt. What I need to do is solve for HF. So let's flip about the equal sign here. So I have N plus 1/2. That quantity times HF is equal to the E that I know. Let's divide both sides by HF. I have N plus 1/2 is E over HF. And all I gotta do now is subtract by 1/2. N is equal to E over HF minus 1/2. Okay, well, N is going to be the E, which is the 1.0 electron volts, divided by HF, which is this number for part A. That's 0.071 electron volts. And whatever I answer, I get, I subtract 1/2 from it. When I work this out, I get E is basically 13.6. Well, again, E has to be an integer, so we'll round up to 14. So N must be 14. So the 14th energy level 13 won't be high enough. That'll be too small. And it makes no sense to have 13.6. So the next energy level that I'll be very close to 1.0 electron volts will be energy level number 14. So I'll have to literally write down on my energy level ladder the 14th one. The 14th one, well, actually the 15th one, because n equals 0 is the lowest one. So the 15th one, or n equals 14, counting from 0, will be the energy level that will equal about 1.0 electron volts. Okay. I got OpenStack's 29.4. Okay, what is the longest wavelength electromagnetic radiation that can eject a photoelectron? From silver. Given that the binding energy is 4.73 electron volts. All right, so now we're in a photoelectric effect problem. Okay, let's see here. Is this in the visible range? All right. Let's go back to Einstein's experiment. And to go back to Einstein's equation, essentially that we know that, okay, so again, what we know here is binding energy is 4.73 electron volts. So what's happening here? Well, we're looking at light in the form of photons striking a material. The anode material happens to be made out of silver. The light strikes the silver, ejects electrons out of it, but in order for it to eject electrons, it must have an energy of at least 4.73 electron volts. That's what it's saying. The binding energy in silver, if you look it up, is 4.73 electron volts. So again, this is from Einstein's experiments. Let's see. We only have one equation out of Einstein's experiment. Okay, the only equation Einstein provided from his experiment was the following. We know that the maximum kinetic energy of ejected photoelectrons is equal to the incoming energy of the light, of the photons, minus the binding energy. Okay, that is the equation from Einstein's photoelectric effect. Okay, that's the equation to go by. Remember, this is the maximum kinetic energy. This is the greatest kinetic energy that you can experience. This is equal to the Q times V of the stopping potential that stops the current, the photoelectric current. All right. So these are, keep this in mind. Max kinetic energy of photons. All right. That's what Einstein's telling you. The max. All right. So that's the equation. And here we're being told that the binding energy for silver is 4.73 electron volts. We're given that information right off the bat. That's a quantity given by silver. So let's rewrite Einstein's equation and solve it for HF. We have HF is KE sub E plus the binding energy. And just doing some simple algebra. And let's remind ourselves now that, remember that in general, for any wave, C equals lambda F. So instead of writing the frequency, I can actually write F as C over lambda. So I can actually write this equation as HC over lambda is KE sub E plus the binding energy. Okay, now let's remember the wording of this problem very carefully. We want the longest wavelength electromagnetic radiation that can eject a photoelectron. The longest wavelength electromagnetic radiation. Well, generally speaking, if you have so longest wavelength basically means minimum energy. Why? Because it's, again, as we see here, the energy of a photon is inversely proportional to the wavelength. So longest wavelength means minimum photon energy. If you max out the lambda, you minimize the photon energy. That's because the photon energy is inverse, the wavelength is inversely proportional to the photon energy. So if you're talking about minimizing the photon energy and still eject the photoelectron, that means your photon energy has got to be just equal to the binding energy and nothing more. You have enough to literally to free the electron from the atom, but you don't have enough energy to give it any kind of kinetic energy. All right, so the minimum photon energy just equals the energy, just equals the energy required to free the electron. But give it no kinetic energy. That means that E photon is equal to the binding energy itself. Or that means that HC over lambda, and again, what is lambda? Lambda is lambda max. Is equal to the binding energy and nothing more. That's what this means. Longest wavelength electromagnetic radiation to eject a photoelectron is another way of saying minimum photon energy, or photon energy that just equates to the binding energy and gives nothing more for kinetic energy. All right, so what we want is that. So essentially, this is our equation. Let me erase again here. So going from Einstein's formula here, we just determined that we need hc over lambda, call it hc over lambda max, is just equal to the binding energy. That's what I get from Einstein's formula. And so what does this mean? Well, I cross multiply, I get lambda max is equal to the binding energy, okay, divided by hc. Well, what is the binding energy? Again, we are given the binding energy is 4.73 electron volts. So for me to do this calculation, I'm going to have to convert the electron volts to joules. That's going to be 1.60 times 10 to the negative 19 joules per electron volt. That means the binding energy in joules becomes 1.60 times 10 to the negative, 7.57. Times 10 to the negative 19 joules. I think I made a mistake right here. I got this upside down. All right, so cross multiplying should be hc divided by be. All right, so hc over be. Made a little algebraic mistake there. So what is this lambda max then? So lambda max is hc. So Planck's constant, 6.626 times 10 to the negative 34 joules seconds times 3.0 times 10 to the 8th meters per second divided by the binding energy, which is 7.57 times 10 to the negative 19 joules. Lambda max we find to be 2.63 times 10 to the negative 7 meters. So lambda max is 2.63 times 10 to the negative 7 meters, or we can look at it as lambda max is 263 nanometers. Okay, that's what it is. So that is the longest wavelength light. It barely does the job. Now, where is this? This is the ultraviolet. So the answer to your question is it is not visible. This is ultraviolet. The minimum, the violet is about 380 nanometers. And so again, this is below violet. So again, lambda max. So the idea is the maximum wavelength electromagnetic radiation that will eject electrons is 263 nanometers. Okay. So again, you want smaller wavelengths in order to have higher energy. Okay. And you have to read these problems very carefully. Let's look at OpenStax 29.6. That one says, what is the binding energy? In electron volts of electrons and magnesium. If the longest wavelength photon that can eject electrons is 337 nanometers. Here we go, longest wavelength again. Okay, so what is the binding energy? Again, this is OpenStax 29.6. What is the binding energy in electron volts of electrons and magnesium if the longest wavelength photon that can eject electrons is 337 nanometers? Okay, so longest wavelength electromagnetic radiation. All right, and so okay, so let's look at this. Again, we know what that wavelength is. What does that mean again? Well, again, you go back to the logic in OpenStax 29.4. So again, we can, it's okay to leverage one problem on another, right? So again, we already did 29.4, so we can use the logic of OpenStax 29.4 to recall that longest wavelength light gives an energy equal to the binding energy. So it gives an energy HF or HC over lambda just equal to the binding energy, nothing more. And that's what longest wavelength tells us. So that means I could say, well, let's see, I want to find the binding energy, right? Well, I found out from that logic, again, that the binding energy in this particular case from Einstein's formula is HC over lambda max. And we're given lambda max. So we're going to get the binding energy, but the binding energy will be in joules. We're going to have to make a conversion to electron volts. Let's try to do it all in one sitting here. So again, the Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Oh, maybe I need two lines because of all the numbers here. Times the speed of light, 3.0 times 10 to the 8th meters per second times that maximum wavelength. We are told the maximum wavelength to eject electrons is 337 nanometers. Well, that's 337 times 10 to the negative 9 meters. Okay, and let's convert. We get our answer will be in joules. Let's say we know that 1 electron volt is good for 1.60 times 10 to the negative 19 joules. We do all that, we find out that the binding energy will be 3.69 electron volts. and utilizing Einstein's photoelectric formula. Okay, let's look at Opus X 29.8. Okay, this one says, what is the maximum kinetic energy? In electron volts, of electrons ejected from sodium metal. By 450 nanometer electromagnetic radiation. Given that the binding energy is 2.28 electron volts. Okay, so let's see here. What is the maximum kinetic energy in electron volts ejected from sodium metal by 450 nanometer electromagnetic radiation, given that the binding energy is 2.28 electron volts? And this is another photoelectric effect experiment. Okay, so let's so again, the incoming light has a wavelength of 450 nanometers. The binding energy or the work function is 2.28 electron volts for sodium. We want to find out what the maximum kinetic energy is, which is Ke sub E in Einstein's formula. All right, so let's erase the board here for real estate purposes. Okay. So Einstein's formula for the photoelectric effect is Ke sub E is HF minus BE. Now, here's the nice thing is, I want to find Ke sub E. So I can almost use this equation out of the box, but what am I given? I'm not given the frequency, I'm given the wavelength, and I'm also given the binding energy. We want to have it in electron volts. Okay, that's fine. So Ke sub E, remember, I can write, I know that C equals lambda F, so I can write this first term as HC over lambda minus BE. And I'm ready to go. So again, Ke sub E is 6.626 times 10 to the negative 34 joules second, as Planck's constant, times 3.0 times 10 to the 8th meters per second, that's the speed of light, divided by lambda. Again, we're told that the incoming radiation is at 450 nanometers. That's a given. 450 times 10 to the negative 9 meters. And again, I want to write everything in terms of electron volts. So let me just convert right now. So 1 electron volt has 1.60 times 10 to the negative 19 joules. And we'll subtract the binding energy. Well, let's just subtract the 2.28 electron volts. Do like that, just like that. All right. When I do that, I find out that the maximum kinetic energy of the electrons is given by 0.48 electron volts. This for your setup. Again, that's the maximum kinetic energy of the ejected electrons. And it's almost straight out of Einstein's formula. I had to re-express the first term in terms of wavelength. All right, let's do another photoelectric effect problem. So I get Opus X 29.12. All right, what's this about? What is the wavelength of electromagnetic radiation that ejects 2.0 electron volt electrons? From calcium metal. Given the binding energy is 2.71 electron volts. Energy. Okay. What type of electromagnetic radiation is this? All right, let's see what we can glean out of this problem. All right, so again, what is the wavelength, lambda, of electromagnetic radiation that ejects 2.00 electron volt electrons? We're going to call that our maximum kinetic energy, Ke sub E. And calcium metal, given the binding energy is 2.7 electron volts, 2.7 electron volts, that's our Be. What type of electromagnetic radiation is this? Okay, so we want wavelength, and once we know the wavelength, we can figure out where that wavelength is on the electromagnetic spectrum and identify. All right, so let's go back to Einstein's formula for the photoelectric effect. So Einstein says that Ke sub E is HF minus Be. Okay. HF minus BE. And of course, we've seen before that I can write this in terms of wavelength. I can write that KE sub E is HC over lambda minus binding energy. Okay, I want, so what I'm given in this problem, I'm given KE sub E. I'm given that to be 2.00 electron volts. I'm also given the binding energy. Binding energy is 2.71 electron volts. All right, and so what I could do is I can solve for this for HC over lambda. All right, so solving this for HC over lambda from Einstein's equation, I get that HC over lambda is just KE sub E plus BE. We can give a numerical value right now. HC over lambda, case E sub E, 2.00 electron volts, plus, keep the math as simple as possible, BE, 2.71 electron volts. So HC over lambda simply becomes, adding these two numbers up, you get 4.71 electron volts. And so what I can write down now is that simply that lambda is 4.71 electron volts divided by HC. All right, so let's transfer this calculation up here now. All right, so what did I get here? I get that lambda, right, is going to be what did I just say again here? Well, not liking something. All right, so what did I just say? I said HC over lambda. This is where I left off. HC over lambda was KE sub E plus BE. Or 2.00 electron volts plus 2.71 electron volts. So HC over lambda is 4.71 electron volts, or lambda is HC divided by 4.71 electron volts, essentially solving for lambda. Well, again, H is Planck's constant of 6.626 times 10 to the negative 34 joules seconds times 3.0 times 10 to the 8th meters per second divided by 4.71 electron volts. But again, I really can't, I need to have everything in SI. So I have to convert the energy to SI. How do you do that? Well, you got to multiply a little factor down here, denominator 1.60 times 10 to the negative 19 joules per electron volt. That gets me everything in SI. All right, when I do that, I find out that lambda is equal to 2.64 times 10 to the negative 7 meters, or lambda is 264 nanometers. And 264 nanometers puts it again in the ultraviolet. That answers that question. It's in the ultraviolet. The minimum of visible light, or the violet, is 380 nanometers. So wavelength smaller than that by this amount is in the ultraviolet.